Hello, everyone. Guess I'm a bit late today. Sorry about that. But looks like we're live now, so gonna be right back. I just need to literally grab a drink because pizza makes one thirsty. Okay. Now we can officially start. Great. So, we're gonna continue with our NIM driver. And I think quite a lot happened since last stream, and I guess I'll show off roughly what's happening in the library so that we're on the same page and we kind of know what's going on, all right? So, first of all, the package is actually deployed to Nimble. You can install it by following the instructions, right? README. There we go. We've got README, where we can see that you can just do Nimble install SurrealDB or include that, and this will install the before CBOR, this temporary version that you can kind of use with all the what do you call them? With all the JSON-like utilities, and it uses JSON RPC and whatnot. And we have updated the list of, what's supported and things that will be supported after we implement the CBOR-based RPC. Okay, and just info that we're working on CBOR, because that's gonna enable us to properly implement typing and get through all those things. So, yeah, that's thing number one. Next, I'm gonna close all the things. Okay, and again, the project went through some restructuring as always. We have basically, I don't remember how much of it happened last time, but first of all, we have two libraries or modules that I'm using to basically deal with integers and maybe a little bit with floats and a few other things during encoding, just to make things a little bit faster and easier on myself. So that's one thing. So we used assign2, endians2, and sequence utilities 2. And other than that, we have all our types separated. And what's important here is that we have surreal value. So this is similar to, like, for example, JSON node is implemented in SurrealDB, in NIM and few other languages, where usually when you deserialize JSON, it gets deserialized into those generic nodes from which you can extract various types of data. Because NIM isn't, it's statically typed, we need to define the types of data. So these are the ones that I implemented so far. I don't remember how much we went through initially, but we have arrays, we have booleans, bytes, floats partially only, because only 64-bit floats are implemented right now. I'll need to look more into how to decode properly, decode and encode 32-bit floats, and then half precision floats, as in 16-bit floats, which are normally not supported in NIM, but we need to at least be able to decode them when they come from the database to kind of make sense of them if data comes in that form. We've got integers, the non and null is implemented. When it comes to, I believe, non, so CBOR protocol supports value of type unknown, which could be considered equivalent of none. But SurrealDB, for some specific reasons, it has its own tag for none. But just in case we get a value that specifies unknown, we're going to assume it's none. And that's what I have implemented here. We haven't got to tags yet, so this is not fully functional yet. We can decode unknown, but we cannot encode none yet. But no, it's all fine, and we actually have fully functional objects. The thing is that with SurrealDB and CBOR, there's a little bit of discrepancy, because CBOR allows pretty much any kind of value to be a key. And SurrealDB, when we're sending objects, they're basically always integers. Even if they show up as a, as an integer, it's also going to be a string. So it's always as a string. So that simplifies things a little bit, because that's the only decoding and encoding that we have to support. It's not like it will be difficult to do any other way around, but it's less cases to test, less cases to worry about, because we have a simple map from string to some kind of surreal value. And of course we have strings, okay? And I have some notes about some newly added, I don't know if documented yet, future and range tags, because today it will be nice to start focusing on actually implementing tags, because that's where all the SurrealDB-specific implementation details show up. All right. So with all those types defined as an enum, we can ignore all that. This is the actual surreal value. It's a what do they call it in NIM? I don't remember what they call it in NIM. It's basically type union or something like that. I think object variance, that's what it's called in NIM, where we have some kind of discriminator. In this case, it's the enum, specifying which type it is. And depending on which type it is, it holds different values, right? So arrays are backed, in our case, by a sequence of surreal values. So this can nest. So Boolean is just Boolean, bytes is just a sequence of bytes. Float is, at this point, always float 64. In the future, we could add another discriminator or just make it something else that could contain float or 32 or 16 or something, whatever we want. And we've got surreal integer, and this is an interesting part, because SurrealDB, I don't know what don't remember exactly now what the limits of values are, but I think we have an equivalent of something like big int or some kind of decimal value that doesn't have some specific limits on the value size. So, and internally, CBOR protocol implements that when you send an integer, you separately specify if it's negative or positive, and then you can just place some kind of integer up to uint64 from 0 to the maximum number for the value. That means that lower values are larger by 1, a little bit further, because they start at -1. And a few other intricacies, so this is non-trivial. And also means that the largest value possible in CBOR doesn't fit in normal int64. We need to just encode uint64 with some kind of flag if it's positive or negative. So that's something we have to do. And then we have surreal none, which doesn't hold any value because it's always itself. The same thing with surreal null. And surreal object is a surreal object table, which is simply an ordered table where key is string and surreal value is the value. So ordered table, first of all, table in NIM is basically a dictionary or a map of, a set of key value pairs. And why is it ordered? So that we can keep the order in which items were added to the map, because it might have some kind of impact depending on how we're sending it. As far as I know, the database basically sorts the keys in the alphabetical order, but maybe in the future it's gonna change, maybe something else. If you want to be in control of how things are ordered, you want them to actually appear on the database side in that specific order. We'll support that because it's an order table, and that's why. Okay. And this way we also don't have discrepancies where we encode something and we try to decode it and some of the keys are different. You know, lots of weird stuff can happen. So this way we can ensure that everything's in the order that we want it. If you want to sort it, go ahead. If you don't have to, there's no need to. Okay. And we just guarantee that the things will be in order you place them in. And the string is just backed by a normal string, so nothing crazy here. And on top of that, we have some operators for basically comparing the values, and we include a bunch of additional implementations of specifics. So for example, for booleans, right? If we go to types of values, we have the boolean. And what it means that we have some basically already pre-made values like surreal true and surreal false. They are currently set as let because surreal value is a reference type. It's not an object type. This way we can just nest them and we can have large sets and pass them around rather than dealing with copies and other weird stuff. And that inherently makes it so that, at least to my knowledge right now, I don't have a way to make it constant. But I'm sure in NIM, in some way, there will be a way to make it constant. So at some point, maybe, we'll see. For now, I'm just trying to make it work in the first place. And then you have, you can take Boolean and turn it to Boolean. For now, I have temporary operator of 3% symbols to take some kind of value and convert it into surreal value. Okay. And then we have like simple like not or get bool to basically check if it's a bool and extract the value. Otherwise, raise an exception. So that's that. And yeah, that's it. And we have the similar for arrays to just convert things around, get the sequences, or for example, to keep adding. I basically added like a quick helper. If you really want to add not to the array that you create a value from, but to the value itself, you can. Similarly, with an object, which here is as a map because I had some problems with naming a file object and importing it. Here we have a few other things where, you can check if there's a key, you can get the key, you can set the key or delete it. Some basic operations just so that we have some functionality in it. And over time, we'll discover what's the best way to deal with that and, refine, iterate. And even things like none have just defined one value, and that value is reused every time we call, to surreal none, even though we didn't give them anything. Because we have the none type and we have the surreal value as none. So these are two separate things. And that's that. And we also have shared. So basically checking the length of things like an array, byte, string, or object. Converting some things to bytes, which is right now just, it can extract bytes or convert string into bytes if you want to, or maybe, extract some float 64 that will get it no matter if it's a float or integer. And hey, turning it also into strings, which we have for floats too. Okay, yeah, so we've got it pretty much for everything besides none. Look at that, we don't have it implemented for none. So off surreal none. We just want to return none, and that's it. There we go, fixed. We'll go over that at some point. This is just for like debugging. And yeah, that's that. And so these are the types. And in CBOR, we basically have a little bit more because we have the writer that we can actually write to a buffer. So we can write some raw integer, you can write float or bytes or whatnot, or check the length of the data. We also have a reader that has a few extra things to deal with, reading the different integers, because the thing is that this is the first time where we actually have to deal with, I actually have to deal with endianness of values. So CBOR wants them to be big endian. So when we read them, we need to convert them to a value that current architecture supports, which I know on my CPU it's little endian, but maybe on some specific device that NIM would be running, it will be big endian, and the conversion doesn't need to happen. That's where we're using the, in this case, endians, and in some other cases we're actually using, probably in writer, we are using somewhere we're using the sequence, endians too, specifically to, like here, that we want to write 2 bytes big endian to ensure that the values are actually formatted in that way. So writer and reader, these are basically, things to store the values, to check for a few things, like, all the low-level stuff. And then on top of that, we have an encoder, where we actually have, encode head. So we give it a writer, what's the major and the length, the byte will be for major and actual argument. Here's those things. It takes care of, like CBOR related stuff, right? Or for writing bools and integers, and overall, like this is the main function to encode, and we check if it's an array encoded this way, if it's a bool, and all those serial values that we provide, we can basically encode, and this is where the code happens. It's not a lot, it's just a lot to slowly figure out how to do it properly. So it's not like we're running a lot of code, it's just what takes the most time is actually writing tests. So we have the encoder, we have the decoder that does the opposite thing. So that's that here. Yep, we have it ready for implementing tags. And, we have false, true, null, none, or, temporarily supporting some kind of integers. Right now, they're pretending to be implemented, but really, they will be re-implemented at some point where I dig into the binary way. I just want to get the whole thing to the point where we can start getting values from the database and start verifying that we're actually doing correct things, or maybe even record some data returned from the database and use that for testing, to write more tests that ensure that the way SurrealDB sends us data is actually correct. And yeah, so that's that. Anything else with constants? We just have one for CBOR break. I think we already had that last time. And not much else here, to be honest. With types, nothing changed here. We just have head argument with all the possible 31 values as handy enum, which I found to be actually pretty handy, where we can just specify as 1 byte, 2 bytes, 4 bytes, or 8 bytes, and a few other things, or like indefinite. So where the magic is happening is actually all the tests. So we have actually tests. We have several folders with tests now. So first of all, we test pure surreal values. Like for example, for the Boolean, there's not a lot here, but we just don't want to make sure that we can create a surreal value that's, Boolean value, surreal bool. We can create it from the Boolean, right? So we just, do true dot to serial bool. We check if this gets properly encoded. We check if we can get the value properly, and for same for false. And we check the, operator as a shortcut. The thing, can we do it with other things? Can we negate it with the not? And that tests that. While we have also a little bit more in-depth things like for integers, where we have a bunch of things, we iterate over all of them to see if we can actually read all the variants of them. So this was actually the most painful thing to implement and actually test. And I found so many little tiny errors. So I'm very happy that I did that. So thank you, Taras. I don't think you're here yet, at least. But anyway, thank you. And we have, testing objects, for example. Can we create it from empty object? Can we create it from a table? Or maybe from a sequence of tuples? Or can we, set and check value to an object? And we have several tests here. So it's all being tested, and that's just for serial value. Then in CBOR, we have decoding. So for example, for objects, can we decode an empty object? And we manually encode it here with some simple helpers. And bam, we check if we can decode with, something where we have map of one element or object of one element with string with key of ID and 4 bytes as the value, right? We just upload, do the bytes things, the same thing, more and more binary data until we check if we can decode even a nested indefinite object where we have a map that's indefinite with indefinite length map that actually holds nested map with another nested map in it. Just going crazy, checking if it's all possible and verifying, decoding. And then also the most important one, actually, encoding, which is a bit more manual because this is what actually gets tested first. Like for something like an integer, we're literally binary encoding an integer and checking if it's correct. There'll be more coming here because I just discovered that the where is it? The RFC actually holds examples of encoded CBOR data items. So we can just check if when we encode, if we get correct values for, infinities, not a number, whatever those are. This is a various data types, basically, like a tag number 24 and a few other things. And this is, I guess, bytes, maps, and all the other things, right? So this will be something that we could do. There's some jump table, which is also interesting. But what matters here is basically that we'll be able to verify over those. I'm already verifying partially for floats, and that's something I'll be doing off the stream, so it won't be too boring. But we have all those things tested, encoded, and at the end we also have test CBOR encoding, where we basically encode, for example, true, and then decode the encoded value and make sure that it's still the same, right? So let's say I will take serial value, which is a map of ID to string, ID to string, ID to a list of strings, right? I'll take that, encode it, and check if it's correct. And then maybe a little bit more complex thing where we have a map that has also integers, that maybe has Boolean, maybe has another map inside of it, and bytes and whatnot, and just making sure that we actually get the same thing. So yeah, we have a somewhat comprehensive set of tests, and that makes me very happy. And I think we will be ready to continue with actually implementing tags this time. So let me just quickly make sure that we have everything that we need implemented. Okay, so we're gonna go to major types. Okay, we've got negative integer implemented fully. So positive and negative integers we have fully implemented, including the fact that this one is from 0 to positive 2 to 64th power minus 1, while this is from negative 2 to the power of 64 to negative 1. So, the same byte just flipped would be stored as 499 instead of 500, right? So those are the little things. We have strings, byte string. Yeah, a byte string. So basically a sequence of bytes, an actual string. Then we've got the array, and we've got the map as well. Just a SurrealDB version because we don't need to support anything else. This is purely for optimized for SurrealDB. We don't have the tags yet, that's what we'll be doing today, and we have major type 7, which is different values and floats. So with that specific one, if we scroll down a little bit, so infinite length, that's actually implemented for decoding, not for encoding, because I don't think we'll be encoding that, really, at least not now. This is about tagging, which we'll be going through today, big numbers, decimals, yeah, there's a lot here. Where is it? Where did it go? I had it somewhere here. That was such a nice little list of possible things. Where'd it go? It was tag. Oh, this one here. Yeah. So for the floating point numbers and values, so basically for the major type 7, these have no use, so they are just saying that, hey, this is not implemented. Then we've got simple value. This isn't used anywhere in SurrealDB apparently, so we're not supporting that either. Half precision is not really implemented right now because NIM doesn't have built-in half precision types, so we'll need to implement it manually most likely. So that's gonna be fun. I just don't have the patience for that right now. I will just try to avoid floats in our initial tests. But 32-bit and 64-bit should work to some extent, at least. And everything that we'll be writing to the database will be writing as a 64-bit float for now. Not a big deal. And again, this is not being used, and this one is simply, a breakcode. Oh, and by the way, these will be separate. We'll cover them in a second. And this is just for reading indefinite stuff. We have it implemented for decoding. We're not using it for encoding. So what matters here now is that, for those values, the simple values, again, from 0 to 19 is not implemented, but we have false, we have true implemented, we have null, and this is what I was mentioning, that CBOR supports undefined, but SurrealDB isn't using it in this fashion. But just in case it's gonna send it to us, we're gonna decode it as none, so we have a start of that. Again, all those are not used. So that's that. So we just need to go to tagging items, which is our major type 6. Alrighty. So major type 6. A tag data item, a tag whose tag number, an integer in a range from 0 to 2 to the power 64 minus 1 inclusive, is the argument, and whose enclosed data item, the tag content, is the single encoded data item that follows the head. And see section 3.4. So let's go there. And let's read about it. So, in CBOR, data item can be enclosed by tag to give it some additional semantics, as uniquely identified by a tag number. The tag is major type 6. Its argument, section 3, indicates the tag number, and it contains a single enclosed data item. The tag content. Okay. So we have major type 6, and then argument indicates the tag number. So we can have a lot of tags defined if we absolutely have to. Like, more than we could ever define as civilization, probably. And it contains a single enclosed data item. So that will be afterwards. The tag content, okay? If a tag requires further structure to its content, this structure is provided by the enclosed data item. We use the term tag for the entire data item, consisting of both tag number, and the tag content. The tag content is the data item that is being tagged, okay? For example, assume that a byte string of length 12 is marked with a tag of number 2 to indicate this is an unsigned big number. The encoded data item would start with the byte listing. So this is major type 6, and this is saying that it's a tag number 2. Major type 6, additional information 2 for the tag number. There we go. Followed by the encoded tag content. So we have major type 2 and additional information 12 for the length. So basically 2 is as a sequence of bytes, and there's 12 bytes, followed by the 12 bytes of big number. There we go. So even though this is encoded just as, 12 bytes or something, we know that this is marked as, we gave it that meaning that if it's a tag of type 2, that means it's a big number. Therefore, we can make sense, create a proper decoder for that specific case to interpret those 12 bytes as a big number, right? In the extended generic data model, a tag number's definition describes the additional semantics conveyed with the tag number. These semantics may include equivalence of some tag data items with other data items, including some that can be represented in the basic generic data model. For instance, the C24101, a big num, the tag content of which is the byte string with the single byte, bam, is the equivalent to an integer 1, which could also be encoded as this or that or whatever. The tag definition may specify a preferred serialization, section 4.1, that is recommended for generic encoders. This may prefer basic generic data model representations over ones that employ a tag. Okay. All right. The tag definition usually defines which nested data items are valid for such tags. Tag definitions may restrict their content to a very specific syntactic structure, as the tags defined in this document do, or they may define their content more semantically. An example for the latter is how tags 40 and 1040 accept multiple ways to represent arrays. Okay, all right, so I guess we have just various ways to specify how we structure the bytes and whatnot, right? As a matter of convention, many tags do not accept null or undefined values as tag content. Instead, the expectation is that a null or undefined value can be used in place of the entire tag. And this is not it's not exactly what SurrealDB is doing, but it's a little bit too late for that now. Section 342 provides some further considerations for one specific tag about the handling of this convention in application protocols and mapping to platform types. Yep, that's what we're doing. We're mapping it to platform types. In our case, the platform is NIM language. Decoders do not need to understand tags of every tag number, and tags may be of little value in applications where the implementation creating a particular CBOR data item and the implementation decoding that stream know the semantic meaning of each item and the data flow. The primary purpose of tags in this specification is to define common data types such as dates. A secondary purpose is to provide conversion hints when it's foreseen that the CBOR data item needs to be translated into a different format, requiring hints about the content of items. Understanding the semantics of tags is optional for a decoder. Yeah, the decoder itself, it converts it, oh, I see that it's a tag. I see that it's an array of, an array of 12 bytes tagged with a tag 2, and that's all it knows. In theory, just the decoder doesn't need to know about it. But in our case, decoder is kind of mixed with the implementation that turns it into the platform-specific data, because it's a bit more tight and specific. So, yeah, but in theory, it doesn't have to. Understanding the semantics of tags is optional for decoder. It can simply present both the tag number and tag content to the application without interpreting the additional semantics of the tag. Exactly. A tag applies semantics to the data item it encloses. Tags can nest if tag A encloses tag B, which encloses tag item C. Tag A applies to the result of applying tag B on data item C. Okay, great. IANA maintains a register of tag numbers as described in section 9.2. Table 5 provides a list of tag numbers that were defined in RFC 7049 with definitions and the rest of this section. Tag number 35 was also defined in blah blah blah. A discussion of this tag number follows in section. Here, know that many other tag numbers have been defined since publication. See the registry described in section 9.2 for complete list. So here we have basically a few examples of which tag mean what, right? So for example, the tag 0, the data contained will be basically formatted as a string. It's a standard date time string, okay? Or epoch-based date time, because these could be two different things, right? There's so many ways to define a date, and using a tag, we can just send specific way of encoding. I will tell that, okay, if you see tag 0, expected date, that's formatted as a string. Or if it's 1, expected date, that's either integer or float, and it's an epoch based date time, right? You have unsigned big number, negative big number, decimal fraction, expected conversion to base 64URL encoding, bunch of other stuff, or encoded CBOR.item. So we can just say that there's a byte string and it's supposed to be encoded CBOR, so you can send CBOR and CBOR, right? Or URIs, MIME message, and many other things, right? So where were we? Yeah, so that's it. So conceptually, tags are interpreted in the generic data model, not at deserialization time. A small number of tags at this time, tag number 25 and number 29, have been registered with semantics that may require processing at deserialization. 25 and 29. 25 and 29. 25, unsigned integer, reference the nth previously seen string. 29, reference nth marked value. Okay, so just some random stuff that we don't really care about because we support only SurrealDB. That's our superpower in this case. Okay, blah, blah. The decoder needs to be aware of and the encoder needs to be in control of the exact sequence in which data items are encoded to the CBOR data item. This means these tags cannot be implemented on top of an arbitrary generic CBOR encoded decoder, which might not reflect the serialization order for entries in a map. We actually do that. We reflect the serialization order in the entries of the map at the data model level and vice versa. Their implementation before typically needs to be integrated into the generic encoded decoder. The definition of new tags with this property is not recommended. Okay, it's not up to us. SurrealDB already selected things. So there's some IANA allocated numbers. These can be used as a convenience for implementers who want a single integer data structure to indicate either the presence of a specific tag or absence of a tag. Okay, we don't worry about that. So then we have basically a bit more about various data types and how they're implemented. So we're gonna look into that. Okay, so that's it. That's basically it. So we'll look at our code. We can probably look into the decoder first, because that's kind of easier to reason about, I believe. So we're gonna go CBOR decoder. So we have the coding of various major types, and then we have major type 6, because tag is literally 6, okay? So here, what we'll need to do is basically check, because we have right now the head and argument available, okay? So the thing is that we need to be able to load the tag number. And in our case, the tag number might be greater than just this value, because this is only value from 0 to 32. Okay, so let's look at how SurrealDB describes its stuff. So here in CBOR, we can see the tags. Okay, tag 0, 6, 7, and whatnot, all the way up to 37. That's already outside of encoding those 5 bits. So we'll need an extra bit. 88, 89, all the way down to 94. Okay, so we could probably get away with just 1 extra byte to read if we have to. But we could probably reuse some of our code, because we already have code that reads the full argument. Okay, so this get full argument, what it does is that, with a head major, we see that we are at the tag. So now we want let tag is reader dot read full get full argument, and we give it that head argument, which is those 5 bits, and those 5 bits at that point determine how many extra bytes to read if necessary, and extract basically an integer telling us the tag number. This is also used for integers and other things that simply make it simply encode the value in there. But here we have a tag, so this will support all the way up to 8 bytes for a tag number. So just in case, in the future we might optimize it, because, let's say, well, to do currently SurrealDB doesn't use tag numbers larger than 255. Room for optimization, right? Because in get full argument, we're checking, okay, if it's between this and that, do that. If it's between this and that, do that. So we could, in theory, replace it with 1if to either do one or the second and not even have other checks. But at the same time, this is, I don't know, this could be actually improved, because this is simply check the value and point somewhere. So yeah, we can just use that, and I will actually, I'm gonna leave it. It's gonna be to be decided. Okay, so we've got a tag number, and at that point, we, depending on the tag number, we'll be able to decide how we want to proceed. Okay, so I already know that I want to go to types here, because we have head major, we have head argument. I think we can actually specify tag, maybe something like CBOR tag. Okay, and this will be an enum. And that's it. We just currently SurrealDB, whatever, tag for the tag number of the CBOR encoded data, whatever. CBOR tag number supported by SurrealDB, okay? So this is where we can just define which we're supporting and whatnot. So we can just go and use what we have here, right? So what do we have here? So we've got, how do we encode them? Name and this. Okay. Sure. So be date time, ISO, string, okay, or ISO 8601. That's our tag, okay? At least it's explicit, and that's 0. Then we've got, so this is none. non-tag. Okay, that's gonna be one. Then we're gonna have I'm just gonna add tag at the end of every one, okay? Every single one, maybe tag in the front of it, because I don't want those to be confused with actual values. I just want to have something in code where I can do just case off rather than anything else and simply get a value out of that. So I've got that part, then we've got what else? Next one will be 0. This is one is 6. Then we've got 7, which will be tag table name. Okay, something to just encode the table name, which I presume is going to be a string. Tag record ID, which will be 8. Tag UUID. Tag decimal, so that's going to be interesting. Tag date time compact. Whatever that means, that's going to be 12. Tag duration 13. Duration string. Okay. And then we're going to tag duration compact 14. Then we're going to have tag UUID binary. Okay, so that's gonna be number 37. So if we have binary, this one will be just string, right? Yeah. That's the differentiation here. Okay, what else we have? We have the tag geometry point. So I'm just gonna go geo point because that's a little bit nicer. So point will be tag 88. Then we have tag geo line. And tag geo polygon. Good. And multi-point. Perfect. Multi-line. Okay. Multi-polygon. And then we have tag geo collection. That'll be 94. And that's it. But not really. Because recently in 202, support for two extra tags was released. And I have it noted somewhere. Where was it now? I don't remember. Future? Wait a moment. Because this is unruly when it's so tiny. Future, future, future. Oh no, we have future everywhere, so it will be range. I guess I don't have it noted here. Where on earth did I note it? I was showing it something in the beginning. Maybe in the README? No. Okay. Not here in types. Oh, maybe here? No. I have no idea where I wrote it down. What the heck? I had it somewhere here. Add notes about range and feature tags. Surreal value. How did it not find word range? Oh, capital R, capital R. So this one, I have this enabled. Sorry. There seem to be new feature and range tags. So this is related to the pull request. And wrong browser shows up for some reason. Okay, so this is a pull request. So the inner bounds inside ranges were not wrapped around tag identifying the range values in the first place, causing them to not be decoded in client libraries. So that's that. And then we also have things showing up in the wrong browser. Add ranges, features, and concatenating to prepared queries. So that's another thing. So this is all within the SurrealDB.js. So I actually have it somewhere here, SurrealDB.js. Do we have the newest? Yes, we have the newest. So we can just open that up and simply take a peek at all the tags. It's just, where do we have them defined? Data, CBOR TS, and we have those. Do we have anything else? Tag future. I'm just checking where we have the tags defined, something that looks like tag definition. Compact line height, perfect. Blah, 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 tag bound excluded. Let's check for that, okay? This is all JavaScript, yeah. Tag bound included. Constants, oh, there we go. So we've got tags here, custom tags. Tags from spec, which is 0 and 37, okay. So that's good to know that these are actually from the spec and not something else. So we'll be able to take a peek at those. We got none. We have the table name, record ID, UID decimal. This one's commented out for some reason, number 11. So let's do the same. Number 11. Okay. So what was it? Oh, tag decimal binary. It's going to be 11, while 10 is string. Okay. Then we've got 12, 13, 14, 15. We don't have 15. 15 is tag future. Tag future. Okay. That's a new one. And then we've got ranges 49 to 50. So tag range. Okay. 49. Tag range is 49. Then we've got tag bound included. And excluded. There we go. So these will be ranges. We're going to add that comment here as well so that we have things organized. Custom tags. Sure. You know what? Let's not have it named as custom tags. We're just going to say that this one is from spec. Okay. From the spec, and we just plop it here, and the same is for 37, so we just plop it here. Great. So anything else? 88, 9, polygon, multi-polygon, multi-line, multi-polygon, and collection. So that's it. Okay, so these are all the tags that we need to implement. There's plenty here, but we'll see how it goes, right? We'll see if we have enough brain power to actually get through this. All right. Okay, so we can move that away. So tag date time from the spec. So something tells me this will be really easy to implement. Opens in the wrong browser. So we go here. And we need to have which one? ISO 86 something. So this is 0, text string, standard date time, C section 341. And 341. Isn't it the same document? Yep. Okay, so 341. Where is it? 341, please. Standard date time string. Tag number 0 contains a text string in the standard format described by the datetime production in RFC 3339, as refined by section 3.3 of RFC, representing the point in time described there. A nested item of another type or text string that doesn't match the format described here is invalid. What? We've got this one. So these points are to section 3.3, which, oh, they construct as an element. Yuck. I do not like that. Okay, so I presume that this is just a normal date like this, encoded as a string. Okay, so when we go to here, you can see that this is date time and it's stored as a string. So let's see where in JavaScript this tag is being used, and we'll be able to see. Case of tag this, just create a date, and JavaScript is that simple because this is supposed to be a string, so we can create a date from that. So I presume in name we can do the same. So let's do it that way. So the thing is that on the nym side, we need to define it as our actual Surreal value. So we're gonna go to Surreal value. We have all those. So we need date time, Surreal date time, right? And here we can specify that if it's of Surreal date time, well, we hold it as a string and that's it. I mean, that's one option. But at the same time, how do dates work in nym? Do we have, because I haven't worked with dates in nym yet. So I would like to first know what's the proper way of working with them here. There are just so many things that we can just close. You go away, go away, go away, go away. So many things. Okay, that looks better. So here we had math. So let's look for standard library and see what we have. We have core, which doesn't mean anything. Nothing here. Collections. I don't think dates will be in collections. String handling. Time handling. Monotimes module implements monotonic timestamps. And times module contains support for working with times. Times sounds a bit more like it, right? The times module contains routines and types for dealing with time using the proleptic Gregorian calendar. It's also available for the JavaScript target. Perfect. Although the times module supports nanoseconds time resolution, the resolution used by getTime depends on the platform and the backend. So for example, JS is limited to millisecond precision. Okay, so we can get CPU time for benchmarking, current time, so we can time and date, we can just say now, and current timestamp as a date time and local time. Then we got UTC, we got timestamp as a time. Oh no, that means that we need to support all the ways somebody defines time and properly format it. I already hate it so much. But it looks like we can just do .utc and screw it, right? So it might be internally keeping track if it's UTC, if it's not UTC, what the local time is. It probably does all of that for us. And that's it. Current timestamp is time. Ooh, so maybe time will be the epoch time. while this is more of a normal datetime. I see. So let's see. The datetime type can be parsed and formatted using different parse and format procedures. So we can parse and we give it a string and a format and it does its thing, right? All those things. Do we have the ISO or something? Time zone. So this is all the basic stuff. Other strings can be inserted, putting this and that and whatever. Something tells me there's a specific way just for the ISO. We'll see. The types modules exports two similar types that are both used to represent some amount of time, duration and time interval. So we'll probably use duration for durations. This section explains how they differ. So duration represents the duration of time stored as seconds and nanoseconds. A duration is always fully normalized. So init duration hours is 1 and init duration minutes is 60 are equivalent. Okay, that's good to know. Arithmetic is very fast, especially when used with a time type. Okay. Time interval represents the amount of time expressed in calendar units, for example, 1 year and 2 days. Oh, since some units cannot be normalized, the length of a year is different for leap years. The time interval uses separate fields for every unit. Oh, I see. That's interesting. How long is a day? Depending on time interval and duration, not always easy. Okay, so great. We don't need to go that deep into it. So what types we have? We have datetime, represents the time in different parts. Although this type can represent leap seconds, they are generally not supported by this module. No big deal, I think. They are not ignored by the datetimes returned by procedures in this module will never have a leap second. Okay. Datetime locale. Okay, so that holds separate. What's up with so many M's? What the heck? Wait, was it in that array here? Described something? Abbreviated 3-letter form for month or full month string? No idea what's that about. Why we have 2 of months and 2 of days. Whatever. Duration. Okay, duration parts. Fixed time unit, hour range, ISO, minute range, month. Okay. Blah, blah, blah. And time represents a point in time. How does it represent it? That's the question. Time format. Parser, time interval. Okay. So a bunch of those. I guess we're just gonna go with datetime for datetime, right? So we can convert them to strings just normally. Converts object to a string representation, uses the format of this, which kind of looks like ISO, but includes time zones. Human-friendly string representation of duration. Blah, blah, blah. So let's just scroll through here because we have all the procedures and there must be something for parsing. Specific types, we can have some operations that we shouldn't worry in this specific library about. What else? Between, convert a quantity of some duration unit to another duration unit. Okay, great. Date time. So this creates a date time. We can specify year, month, and all that fancy stuff. Okay. And a specified time zone. And we can just do .utc and it's just gonna correct it. Zone is UTC. Oh, look at that. Great. So we've got that, days, div, epoch time. Look at that. So gets the time after the Unix epoch in seconds. It is a float because sub-second resolution is likely to be supported. Okay. Unsuitable for benchmarking. That's still better than now. Use mono times, get mono time, or CPU time instead. Okay, makes sense. And then we've got a bunch of format, right? Just a lot of them. Either as a string with some locale. Yeah, nothing crazy here. From a value, from Unix, from Windows time. Okay, this is not gonna be fun at all. And we have multiple ways to init datetime. Deprecated, use datetime. So they're all deprecated. Okay. Makes sense. Init duration. Okay, now just get the current time, that's it, and we've got parsing. So again, parsing various things, nothing specific to ISO, which is surprising to be honest. Now UTC offset is parsed, then input is assumed to be specified in a zone time zone. Okay. Parse time, seconds, and to parts, to Unix, to all the stuff. And then we're going to UTC. Just on its own, get time zone implementation for UTC time zone. So it returns literally a type zone. Shorthand for something in zone. So it basically checks, converts it to specific time zone. And shorthand for pretty much the same thing. Okay. Just on time instead of daytime. Okay, I expect to have ISO helpers. But apparently not. So it looks like we'll be parsing the thing into daytime. So let's just start with that. We can just simplify our implementation just to that for now. And continue in the future with, improvements. So it'll be daytime. So for daytime, we'll need to import standard times. Okay. So CBOR type daytime. I hope it doesn't take too much data because then everything else will continue. But for now, we just want it to work. And then when we're comparing datetimes, we just compare them. And I guess it's gonna work. I hope it's gonna work. All right. So that's that. And what is it complaining about? Can I have side effects? Really? Does that have side effects? Apparently so. What? I did not expect that, but maybe it's gonna go away after we actually compile it. Okay, so that's part one. So let's actually add some kind of implementation. Datetime. Okay, so we create new value file, datetime.nym, and we can use something like a string as an example. Okay. So this would be our example of ways that we can create. So basically we would want to have an ability to turn a datetime into surreal datetime. So proc to surreal datetime. We'll take datetime. There we go. And just create surreal datetime with a value here. And then that's it. So that's good. This is basically the same thing. Um, and proc get datetime. And this will need to check if it's datetime. Otherwise, just throw an error that, sorry, we can't convert this into a datetime. So the thing is that we should be able to create a datetime not only from this object, but it would be nice to be able to create it also from a string, as in to parse it or something. In theory. But at the same time, the only place that would happen would be in the decoder, right? When we get encoded something in this format, we need to read it up. So maybe not even implement it here. Just whatever. That's it. So let's save that. We have it imported. The only thing we need to actually modify is that we need to, in shared, we need to add that. Or no, we actually don't have to. This is in serial value, right? So we already have all the tabs. Okay, never mind. So all that works. So now we can simply go and to write some tests, okay? Because that's what we're doing most of the time, writing tests. So new file, test, surreal value, datetime. Okay. Again, we can take our string as an example of something of this sort, where we can just copy first few lines and take it from there. Datetime. Can create from a datetime. Okay. So let datetime is, for example, now, right? Because this is supposed to return us datetime. We just need to make sure that we have times imported. Okay. Now we can see that it's a datetime. So serial value will be just converted to datetime and check if it's actually turned into that, and if the get datetime is the same thing. And also, sort of the second one will be just, we're gonna run this operator over it because it's supposed to be same thing, both of them. Okay, and this will also check our comparison algorithm. Okay, so I want to do this and then that. Great. So then will be test can get, I mean, we already tested everything here, so this might be it for now. What's this? Sure. So what we want to do now is go to our Nimble, where we have all the tests described. What I'm gonna do is I'm gonna make another one just for datetime, and I'm gonna save it here. Okay, these are all the tests. This one doesn't exist yet, so it's ignored. So what I'm gonna do is I'm gonna go here and say run the current file, and we expect this, but we got float in serial value. Oh, because we're missing comma. There we go. Fixed. Okay, we passed the test. Not a lot needed to happen here. But that's really it, because we checked if we can compare, if we can do a few other things. It's not very comprehensive, but it's a start. And we don't need to have sequence utilities here. Okay, perfect. So what we can do is just go and say, we'll get to tags in a second. So yeah, sure, let's define tags. Define SurrealDB tags or CBOR tags. Okay, and then we've got the serial value. So this is basically simple implementation of the datetime. And in shared, we also need to quickly add the other abilities. I'm actually not testing too much of the shared. Length doesn't make any sense. 2 bytes doesn't make sense. the only thing we want to print it out. So this is where we would kind of want to print it out as the ISO of datetime. Print it as what's the name of it? This. Okay. Datetime val. Is it gonna just print itself out like that? You serious? What is this string? Sure. Can I see examples, please, or something? ISO tackles this uncertainty by setting out an internationally agreed way to represent dates. Year, month, date. Therefore, the order of the elements. Yep. Okay, so this is the format. And can be used by anyone who wants to standardize present dates, time of day, coordinate, reversal time, local, and everything else. So when we're printed, we just do UTC, right? And format. Is it really that? What the heck? Examples of this. Dates. History, and we have examples. Combined date, time, presentation, duration, time intervals, usage. Okay, no examples. So we have the plus and the thingy. I hate dealing with dates. Absolutely hate it. As you can see. So let's just check again here in NIM. Because we had .utc, so that's the NUTC. So we can just .utc, right? Now plus duration and all that stuff. So what's the... Come on, where's this thing? I want to scroll this part. This thing. If I give it datetime, converts datetime object to a string representation format. This, so it uses the time zone as Z's instead of some other stuff. Read, there's no link to the full standard. Thinking. Not really. That link doesn't lead anywhere. Oh, now loaded. And what the heck? You can't even read the standard. Well, here it shows with Z's, here's with pluses. What the heck? we might just get away with the normal representation of that from nym. To do check. To check if this actually works, but yeah. Okay. And for length, we can't do that. None of the other ones. Okay. So that should be it. So let's continue with this thing. We've got shared, fixed. No changes here. We added it here, and we have that. Create, surreal date time value and tests. Okay, we define that. So now the next thing to do is create another part of it, which will be encoding. So we want the encoder. Or do we want decoder? Let's tackle the encoder first, okay? So CBOR encoder. And we basically, when we encountered the of serial datetime, we want to be able to encode it, okay? So in this case, I want to just encode the tag. So we're going to do writer encode head. So what encode head allows me to do is encode the major type and the length, which basically is a UN64 number that I want to encode. That usually means what kind of length of the value I want to encode, that, whatever. But in this case, I might just specify that I want to encode number, 20,000, and it will just use the optimized number of bytes to represent the value. In this case, for tags, we're using exactly that. So we can just say that we're going to have writer.encode head, and this will be tag. Okay. And we do tag datetime, this thing here. And I would like to be able to avoid this UN something. So can I do UN64 here? Oh no, this doesn't like it. What if I'm gonna say use 64 and just put it at the end of every single one just for fun? Is that gonna work? Possibly. Possibly. So I'll assume it works. Although it might not like it. We'll see. And besides that, we basically need to write those things, and this needs to be string. So I would need to have same implementation as when I'm writing strings, right? Length, and in this case, I'm just gonna write the bytes. And I would take the value to bytes, which is not that much fun. But in this case, I can just use this part. So let bytes is we take the value, which is the date time. Wait, get date time. So let date time is this thing, okay? And then we can just encode the date time .utc that we convert to string. Okay, just make sure it's UTC or whatnot. Or do we even have to? We probably don't have to, because time zone is good enough and the database will take care of all the comparisons. We're good. So we just take date time, we turn it into string, and then encode that string as bytes. Basically cast it to bytes. So then we can just write the bytes And that should be it. We cannot, because we first also need to say how many bytes we're writing. So we take the bytes, and this will be the bytes length. There we go. And this keeps complaining. We're gonna see in a second. So this goes down here. So encode how many bytes it's gonna take. And bam. All right. Okay, I can live with that. No, not the most beautiful code, but it should be enough. Okay. I can 100% live with that. So next, we need to test that. So we go and create new CBOR encoding test. Test CBOR encoder datetime.nym. Okay. And we can probably open up some example of encoder, like for string. Okay. So this is an example. And we know that we'll be dealing with times. All right, so that's one thing. Date time. So student code current date time. Okay. So let's get current date time is no. And let bytes encode and we do check bytes. Oh, so I actually don't want to do current time because I want exact bit representation. So let date time is what did they say in nym that I was supposed to use? Because we have all those inits here somewhere. It says, can you wait? We're gonna use date time. Oh, so there's something already defined as date time. There we go. And we specify, wow, all those values. Oof. Sure. So will be DT value. Okay, that's what we're gonna call it. Datetime value. So it'll be datetime, and now year will be. Well, let's pick today's date, 2024. Month will be. What is it? September. Will that work? Possibly. Can I click on that? mseb. mseb. Okay. mseb. Cool. And month day. So it's just a number, which will be, in this case, 27. And then we have hour, which we'll encode as 10, so it'll be 22. Minute will be 33. Okay. Zone. Oh no. How the hell do I define the time zone? Let's do UTC. Okay. UTC time zone. Okay. No big deal. Nanosecond 0. Seconds. 15 nanoseconds. Bam, 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 bam. Okay. No idea how I'm supposed to encode it even. Hmm. And that. I'm gonna do it this way so that I can have it my way. Year, month, day. Okay. And it shows error type for some reason. Do I need those or should I have commas here? Because this is very strange. Okay. Hour, minute, second, nanosecond, and zone. I really don't know, but we'll see. So echo date, time, and etc. Right, and this should just print it out properly. So we'll see how that goes. We encode this thing, and we'll need to check bytes. So this would be type 6, and this is type 0, right? This is 0. So and here we need to have also 0. Okay, that's our type. And this would be some kind of encoding right now. I'm just gonna let it be random. We're gonna decide it once we know what it's actually supposed to be printed out as. Okay. So can I just run this file? Or what is gonna happen? Is that an improvement? Wait, I have this everywhere. Are they all supposed to be just those? Or they are supposed to be equal signs? Forgot. Now type mismatch. Okay, so it doesn't like that an encoder, and the encoder, we didn't convert it to UN64. Okay, now it should be happier. Now this file. Okay, and type expected. What? A type expected. Oh, so these, I guess, need to be all equal signs. That's what it is. Yeah, I'm mixing up languages. Every language decides to do it differently for some reason. Oh, now it decodes the date time, so it should work. Whew. And current date time. Nope, DT value. There we go. Getting closer. Okay, now it's complaining that the date was wrong. But datetime etc, we have it rendered as this, and it straight up ignores our nanoseconds. I guess that's not a problem, although at the same time, how does the SurrealDB deal with that? So we're gonna take a look at that right after I take a short bathroom break, so I'll be right back. Alrighty, I'm back. So, you know what? We're gonna ignore the nanoseconds for now. We're gonna all set it to 0. And we're just gonna encode this part for now. I'm just gonna do that for the testing purposes, but first here will be to do redo tests after getting proper test data. Okay, because right now I don't know how exactly we're supposed to encode that. So I figured, you know what? Let's just have this encoder here for now. But what we're gonna do is we're gonna make a decoder that basically prints out whatever string we received from the database, so that we know exactly the format that the database is expecting us to send back. Okay, and I can just do some more digging into how to properly encode it in ISO format. We don't need to deal with the dreadful date times here. This is something we can do over time. And hey, maybe if somebody wants to help out, especially during the upcoming Hacktoberfest, that would be great. Remember, all the code is public. That's the whole idea of those streams. We do public stuff. So what the hell I want to do? String to hex. And which one was it? This one? No. There was some nice that I liked. Why are those results so different? Hell no. Online string tools? Nope. What the hell was I using? I have one that I like to use for this specific reason. No. I search for UTF-8 to hex. There we go. There we go. I can paste my string and say that I want this fancy thing. And this will be where we're checking that this is our first thing, and the rest of the bytes are basically this. I just go select all those, put comma at the end, and this is what we're expecting it to be encoded as, right? Oh, we also need to add one extra byte that says that this is a string, right? So 0b, string was 0 and 1 are numbers, 2 is bytes, 3 is string. So it'll be 0, 1, 1 for number 3. And then how many characters we have here? How many is this? This is 20. Okay, good. 20 will fit because we can fit 23 numbers here actually. So we'll just do 23, and we know it's I'll be just doing this on the side. It's gonna be a little bit easier for me to continue with that. 10111. Wait, why did I type 23? 20. 0, 0. There we go. 10100. There we go. So this should be, oops, I put in a wrong spot, of course. 10100. There we go. And do I need U8 here, or I mean, I shouldn't need it here. Happy? I mean, it should be happy, but I shouldn't need that in the first place. Okay, never mind. So that should be it. Yeah. this should be our encoded thing. So we need to check if it's actually those bytes when we encode it. So let's run this file and see if that actually works. And no, it does not. This thing. So we just open up a new file. So that was this one, and then we've got this one. And we've got oh wow. What the heck? Tons of differences. Why this string is so long while the other one is so short? What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 16, 17, 18, 19, 20. 1, 2. Oh, we've got extra 2. I mean, the first one was fine. The second one is not. We've got 2 different numbers. So I might be just doing something simply wrong. So this is what it was encoded as, apparently. Yeah, it's the same thing. Got all the bytes here. All the way to 5A from all the way to 3230. Yeah, so all the bytes are here. The first one is supposed to be tag number plus major 6. Okay? So the next one is major 3 and length, which in this case is supposed to be wait, I have it here, right? It's supposed to be 20 characters. Okay. And 20 is last 5 bits 10100. 10100. So that's good. Do I need to explicitly specify this U8? I mean, it doesn't make sense if it wasn't obvious. The first one is specified, so that's strange. So what are we doing when we're encoding it? We encode the head with this value, and this value is 0, so that should be just 1 byte. This whole thing. And then this thing, we encode the head to be string of that length of 20, which should be again 1 byte. And we write the bytes, which is stringify the date time, just like we did in the other place. Echo number of bytes. And I just need to print that out. I need to know if it's the same number because something's not right here. And I don't want to... wait, I'm testing the wrong thing. Too many things open. Come on. Oh. Test current file. Of course, we are supposed to have this part. Number of bytes is 167. What? Oh, maybe it's actually something different. Because, I think we're onto something. So here, when we're echoing it, we give it a DT value, right? This is date time. And then we're taking that DT value and shoving it internally as the same value. So that's fine. But when we're printing it out here in the encoder, we just do that. So let's do let date time string. is this. Okay, it's a string. So we can turn it into bytes. But let's do echo datetime string, because they might just be encoding them differently depending if it was passed already as a string or something else. So I want to see that, if there's that discrepancy. So datetime as string, when we just print it out, it just prints this whole thing. What the heck? Oh, wait. Because encoder doesn't know how to deal with times. There we go. Now we'll have a specific, a specific formatting for that thing. Why am I running this thing? What the heck? This, please. And now it actually passes it because both are returning the same thing. There we go. Huh. How interesting. So we can just skip that part and leave this way here. And the encoder, we don't need those weird shenanigans with wherever that is. Datetime. I'm gonna make that a little smaller because it's just so hard to work with when it's so massive. So now we can just relax and just say, you know what? This. We need to print out how many bytes and whatnot. When we run it again, it's gonna be clean and tidy. Bam. There we go. Great. Okay. So that works. We can encode some current datetime. And let's stop at that right now. What I want to do is just quickly touch on the decoder. So let's go to decoder. And we'll attempt to convert it into some kind of datetime. But with parsing, it should be good enough, I think. But what matters the most is that we will have the first thing. So here we're getting the tag number. So case tag. So let's do dot. Size CBOR tag. There we go. Convert as CBOR tag. So case tag of tag datetime. Okay, we want to take care of that one. So let bytes is. So here we're going to decode it, right? So we can read those bytes. Do I have a way to read a string instead? Not really. How do we read strings? Read the bytes, do this and that. Okay, good enough. We can just try to copy paste it and see what happens. So in our case, if we see that this is a CBOR tag, that means we already read a proper number of bytes and everything. So we're good. False is unsafe. We'll be fine. Calm down. So yeah, we extract how many bytes from the next. Oh, so we need to first get the number of. So we need to again read the head, which was basically this thing. Where are we? Here. So we'll just say ignore the head major. I mean, let's not ignore it. When we need to read it, so let's read it, okay? Yeah, so string head and string argument. Okay, and where did the head come from? We gave it here. So do we have another one or something? Come on. Decode CBOR reader, so we just do read head. Okay, there we go. Reader, read head. So this is gonna be this thing. So we read the head, and if major is not string, we just need to raise exception. Express string for datetime. For a ISO 8601 datetime, and we'll just say in parentheses tag 0. Okay, because that's what's in here. Because if it's not that, it's just a a massive error. But is not string. I don't remember what the hell is the proper way to do it in nim now. Oh no. Major is not whatever. Head major. What the hell was head major? String. Yeah, capital string. So in theory, this should be correct. Oh, that's what it is. AI just isn't aware how it works. Okay, so that's good. That's good. And then we can say numbers of bytes. We can read it from this string argument. And this, if it needs to, reads more bytes. And therefore, we can extract that number of bytes and turn them into a string, which in it's a real string, we just do this kind of thing. So bytes. We don't return it into that thing. Let datetime text is this, and we can do echo received datetime, and we're gonna print it out extracted. This will be for our purposes, so that when we actually receive data from SurrealDB, we can print it out and we'll see what format it is before we even, let's say, fail to convert it to datetime. So return parse, and yeah, what was the format again? Let's assume the same format. We had it somewhere here, this thing. So correct, correct, and correct. We have hours, minutes, seconds, and ZZZ, which I presume is gonna be correct. Okay, so that's good. Do we have times implement? No, we don't have. So times, and that should make it happy now. Case tag. Okay, and this isn't happy because not all cases are covered, of course. So right, this is gonna be it. We wait, not even return it. So let dt is this and return dt to serial datetime, and that's how we return it. Otherwise, we just raise exception tag not supported, and we give it which tag. Okay, great. What is the problem here? This expected, but got that. Yes, because we need equals. Oh, we already have that here. Oops. Good enough. So this is unreachable. There we go. We just keep some room between them so that we start having it a little bit easier to navigate, and I don't think we will need to split it into multiple files. I don't think we'll be growing that much anymore, other than a little bit of, you know, those tags will take up a little bit more, but we don't have like million tags, so we should be fine. So what I'm going to do now is I'm just gonna leave this untested. The only thing I'm gonna do is go to SurrealDB.nimble, and I want to basically mention that I want the encoder tests for datetime included. We already have one. I'm just gonna add to do. Needs more work. And then we're gonna define the same thing, but for the decoder. But it needs implementation. Okay? Because it's not really implemented yet. The same thing here. So that's why this one is just commented up. But at least we have a note that, you know, don't forget to implement it. So I want to just quickly go through the rest of the tags that we need to implement, and implement like the most important ones, so that we can actually finally start connecting to the database and see if we can actually get something out of it. So datetime. It shouldn't be coming with every single value, I think, so we'll see how it goes. Then we have tag 6 none. That's an important one. That's a very important one because it's being sent in so many ways. And we already have partial implementation for it, so let's do that. Tag 6. So we already have the value, serial value none implemented. So I want the decoder first or encoder. Let's do encoder because we don't have that. So as you can see, we have an encoder for null, but not for none. So off serial none. And what we'll be doing here, it's not gonna be simple. It's gonna be tag and 6. Okay, tag number 6. And then we need to give it a value. But what is supposed to be that value? Tag number 6 represents a non-value. The value passed to the tagged value is null, as it cannot be empty. So we just need to encode null in here, which will be writer, encode head byte, which will be simple. And what is the null value? 22. There we go. Takes null as tag content. There we go. So that should be it, literally it, to encode non-value. All right. So let's just write a simple test for it so that we have something started. Encoding, new file, test, CBOR, encoder, null. Sorry, none. Okay. I can take an example from the null so that we can follow as quick as possible. Okay, just encode none. And I'm just gonna do this none. This should be capital null, because that's how it's everywhere in documentation in SurrealDB. So writer, encode none. That's the type that we have. That's actual specific value. And then what? We want to basically check if the output is what we want it to be, which is a tag of number 6. So 1, 2, 4. So it will be, I believe, wait, shift 1. Oh, that's N on that keyboard. Huh. What the heck? I don't know that shift works with number keys like that. num, but interesting. But this should be 6. Okay, so that's the first one, and the second one is supposed to be exactly the same as here. Okay, it is always supposed to be 2. So I wonder if we could actually, in the encoder, just say that, where's our encoder? Here. For something like null, do we need to do encode head byte and write row and call this thing that then assembles it with all those? That's kind of pointless. I would like to do encode byte or something. Do we have something like that? Encode byte, encode head, encode bool. Not even code. We can just do writer, write byte. Write row u integer. There we go. So that's all we need, right? So we should be able to literally just encode this. Have that. This is for null. We don't need this. This is simpler, this is faster, hard coded. And we do the same thing, just with bytes. And we have row u int, but if we are going to do with we have write bytes. Yes, we can just give it an array of bytes, and it's gonna use a little bit faster way to write it instead of, because it won't be expanding, well, by 1 byte first, by second byte second. It's just gonna expand the array only once, or the sequence. So here we could just do writer, write bytes, and we're just gonna have an array of 2 values. That's gonna be second value. Okay. The first value we actually need to get from the test. Which is kind of funny. Let me just make sure that I'm encoding the number 6 properly. 6 is 0110. 0110. Okay, so we're good. This is 6 as well. Okay, all right. So this should be faster than those two things. Optimization, right? Okay, so that's good. And we could probably just put it in our constants, because that's kind of handy. Constant null byte. Okay, do I have it copied properly? Yes. And constant non-byte, and that will be an array of 2 elements. Correct. And this one will be the null byte. Here we go. We're reusing stuff. Awesome. Great. So that means inside our encoder, we can say this is gonna be non bytes, and this will be the null byte. Null. Wait, what did I call it? Null byte. Yeah. And this doesn't include what is it? Constants. So it's in here. Okay, now it should be better. A little bit faster. Test suddenly becomes kind of pointless. But at the same time, yeah, I will not even use the values here. Just please be that. And I also want the, well, there's no other way to encode it, so what else do I check here? Writer encodes serial non to be the same thing, and then None. Two serial. Yeah, like bunch of variants. Sure. Let's test it. And we have no none because we're importing no. None. There we go. Okay, so we can encode none. Hopefully. We'll see soon enough. So that's good. Constants can go away and we can basically, the none is actually implemented. There we go. So decoding none. Yes, please. Why do I have a feeling that we already have decoder for none? We have a decoder for none. There we go. Undefined byte. What? Oh, code undefined as none. That's the first one. And then it will be test the code. Non-tag. Whatever. Encode null tagged as none. There we go. So, here we give it this thing. All right. Sure. This looks good. This looks somewhat good. We decode it. We check if it's serial none, and we check if it's exactly the same thing. We run it and we check if it works, and it does not work. The second one is not happy. Tag not supported. Oh, because we didn't put in the decoder yet. That's why. Tests work. So we've got our tag of date time. Now be off tag none. And well, if we have tag none, in theory, we need to read that second byte. So it will be reader dot read uint 8. Okay. So let's say let null should be null byte. Okay. And there's exception, otherwise just return serial none. And that's it. And that means we need to import our constants. And that should fix our problem. So let me just collapse things like integers, bytes. I'm gonna collapse string as well, array, map. We can open them up when we need the same thing with simple. Yeah. Anything interesting here? No. Okay. This should make code a little bit easier to navigate. So now that we have that, any decoder, we should have both working, right? Okay, both are working. Good. So let's start pushing our changes. So first of all, we're gonna take out the decoder in terms of the time. So let's just say that we have, we'll couple them together. Encoder types. Sure. This thing here. And we have a bunch of tests. So this will be initial date time support. Full no support. Sorry, none. Okay. Push. And now let's actually run the test of all tests. Run test. I just want to see if we're actually gonna have everything passing. It's good to run it from time to time to see if we didn't break anything along the way. And yes, that is a lot of tests. Some of them run, hundreds or thousands of iterations testing various values. And all those warnings are actually from different module that tries to support stuff that we don't need. I haven't had a need to strip in a code really, so that's why. I need to take a peek to how to disable those warnings. They're kind of annoying. Okay. We're getting there. All right. That works. So that means we can actually go over to the last one. The overall encoding, where we can just specify a little bit more fun things. In our case, I want it to be, because who with strings, arrays and whatnot, objects, all the basics. And after that, I want to have additional. Do I have something about null and non? There must be something somewhere. No. So let's do test encode and decode non. So we just take the non value, encode it. We then straight up, because this is gonna encode and wait, writer, and this returns a writer. Oh yeah, it returns writer because we didn't give it one, so it's gonna return a fresh one. And for writer, we can get the output, which is in our case bytes, because we just encoded it into bytes. We decode those bytes, and then we basically can check if it's actually real non, and it compares to an existing value. So that's test number one. And then at the end, we're just gonna say test encode and decode date time. Okay, so here I want to just take now, encode it, decode it, and make sure that, let's just let date time value is now. Okay, we're gonna just do that. And we're gonna just reuse it here so that we get something half decent. You want to encode that and check if after decoding, when we get it, it's the same thing. And I also want to check if we're gonna say UTC, if we're gonna decode this thing, if we're gonna get the same result. Wait. Let writer 2, serve value 3. Huh? Datetime value 2. Oh, what the hell am I doing? Let writer 2 encode this value dot UTC and to serial datetime. There we go. Decode and check for those. Okay. Let's run this file. I want to see what the hell is gonna happen. Although we probably need to import time. So let's just run this file because this is the only thing we modified, and it identified none. There we go. We need none and null. Okay. So we received this one. What's up with those ends there? Okay, so we got some problems with date times. Something's going on here. So that's probably in our decoding. Because, I mean, it shows that we received this thing. So serial value get datetime value is slightly different. So here we're showing that we received this thing 2046-400, and this was the same thing. So I'm not sure how to compare them. Yeah. So let's do figure out how to properly compare date times. We'll get to that, but for now we're just gonna say format this thing and format that thing and compare them this way. Okay, we're gonna do the same thing here. And this should be good enough comparison, I hope, to just make it pass, or no, or maybe not. Oh, wait. Check failed. This thing was that, while this thing was that. Oh. Really? So I guess we might have a situation where we lose some information. Let's ignore that part of the UTC. I'm not sure how that works. Just simple. Okay, simple datetime works. All right. That's good. What if I'm gonna try it without those weird comparisons? Is it gonna be still same datetime? And valid indentation. What did I do? Extra parentheses. That's what it is. Yes, that is failing because we have some weird stuff going on. So we'll just have that. We have this, not full implemented datetime, but at least we have non-working. So we're just gonna do. Where's our get cracking here? So basic datetime encode decode test. Non-test. There we go. We've got those. Moving forward. So now what is the next tag that we absolutely need to encode? Next tag will be table name. So I expect lots of table names to be returned as that format. So a table name represented as a string. So in this case, I actually want a separate type for the serial value for the table. I think that's pretty important. So when we go to the serial value, we can add table, serial table. Okay, just like that. This will be just the table name. And what's gonna happen here? We add of serial table, and this will be table value. Table name. Right? Do I need to import it from somewhere? Import table name. I think that's it, right? We have table name, and it's just a distinct string that we can create this way. And this way we can store this value, and we just need a way to create that and compare that and do a bunch of other stuff. So how do we do that now? So I want to create new value. This will be table.nym, because that's gonna be the serial table. And I'm gonna take string implementation as a for comparison, so that we can kind of move quickly. Proc to serial table, and we give it table name. Okay. So we just do that. Okay. but I also want table val name. Oh, we need to quickly go to here and wait, we already imported that, so I guess we're fine. We have also proc to surreal table where we give it a string and convert string to a surreal table, and that's it. We just straight up convert it here, no big deal. In the future, we can add some more checks, but in this case, I just wanted a separate distinct type and nothing else. So we have proc. We just do this table name and the same thing here. Okay, good. Good enough. And then we have proc get table, and it just returns the table. That's it. No big deal. Mostly copy paste, and we need to import it here. There we go. So let's test it out. I need to be vigilant about creating those tests. New file, test, surreal value underscore table dot nym. And we can just compare it to similar value for strings. So this will be table. Can create from an empty string. I mean, that's something that I wouldn't want to be able to do, but so can not create from an empty string, and we're just gonna discard it with to do implement, because I want to make it somewhat smart when we're converting a value to a table. But that will involve a little bit more changes so that it just goes throughout. For now, we'll just have the thing there, but not there yet. So test can create from a table name. So let table is tb, and we're gonna call it user. Okay. Tab key, what the hell? Table tb user. And we need to import types value, comma, table name. There we go. So we can create a table, and well, we should be able to do that. It's all correct, and it's all good. The other one is with the same thing. There we go. Can create from a string. So we just make it user, and we should have the same thing. Good. And we can get it. Bam. And so we maybe product, right? There we go. And we're not implementing any getting string value or anything. We just have those simple tests. And I think this should be enough to just make sure that we can do basic things. All cases covered. What? Surreal value. Oh, we haven't implemented? What? How did that happen? I thought we implemented that. Oh, for comparison, of course. Of surreal table, we just need to compare the values, and that's it. So no big deal, not a big deal here. And do I have comparison for that thing implemented in table name? Yes, I do. Great. So that's one, and we need to go to shared to also get the things like length. So off surreal table, we'll just get the length of that thing. Table val, I don't think we can do that, so string. There we go. We couldn't do that with date time because it doesn't make sense, nor with none. Okay, good. 2 bytes, we ignored that. Although it could happen, no problem. Right? Sure. To float, no, and one would want to print it out. It's gonna just turn value dot table value dot string. There we go. Okay. I think we have all the basics done. Yeah. So let's go back here and run the current file again. Oh no, redefinition of the previous one. Oh, that's true. So we can't do that because string should be just going into a string, and that's it. If we want explicitly convert a string to a serial table, we need to use that one. Okay, makes sense. We had the 2 bytes. Get string. Oh, we had it also made to serial string from just those bytes. I'm gonna implement similar things. So it'll be, it won't hurt, right? Proc to serial table, open array of those, and that's the text, and we just turn it into table name. All right, that's good enough. That's good enough. It should be passable, I think. Ah, yeah. I wonder if get table we did somewhere. Get table name. Sure. Instead of get table, we just do get table name. Let's run this thing. Please work this time. No. Exception cannot extract table name value from a serial string. Wait, what? Get table name. Me getting confused. You go away, you go away, you go away, you go away. You go away. And you go away. I want my table. So when I do get table name, give it serial thing. If it's not that, can get table name value. Cannot extract table name value from a serial string value. Oh, because I'm doing probably the wrong conversion there. Yep. That's what it is. I'm doing this thing. I mean, this is good, but from a string, I cannot do that because this one won't work. Only this should work. Can get the table name value. This is good. This is dot table name. There we go. Execution of external program failed. Product user. Oh. Wait a moment. what is the point of this? Check surreal value 2 dot get table name is listing, please. Let table 2 is dot table name. This way we'll have 2 different variants, and this will be product. And therefore, everywhere we see this, we just do this. Bam, bam, bam. And we have a pass. Finally. Finally. After 30 years of trying. Okay. All right. So this basic thing is passing. So now let's implement encoding it and decoding it. That should be really straightforward because it's gonna be just like with a few other things. It's basically copy paste, few little variants. So encoder, and we have our encode somewhere here. Okay. Where is it? So we want encode table. I mean, of surreal table. So just like the string, we just grab all that. Okay. Get the bytes, which is the value. 2 bytes. Yes, we should be able to call it because we defined that for the surreal table. So that's great. So as we have it 2 bytes, here's just encode this. So that's not exactly it because we also need to do writer encode head that we're gonna do tag, and the tag of this thing is as a string. So tag table name and byte. For null, we were just using a constant, so that's that. This could be turned into a constant at some point. So at some point, we'll just go and on like crazy vendetta for optimizing it the hell out of it, and we'll just convert a lot of this stuff in the future. For now, we're just making sure that it works. So, where's our date time? Encode head. So this and length. Okay, so yeah, head, not head byte. Encode head and table name. .un64. So that should be good. Do we need to do anything else? Tables, times, constants, writer types. I think that's it because we don't really need to deal with any internals here. We're just using external stuff. So we should be good, I think. Yeah, that should be it. Okay, great. So let's also touch on the decoder. Our decoder just unfolds everything every time. So of tag table name. So now what? So we just compare the tag and it told us that it's that. So we basically need to read the string. And for the string, we're basically grabbing this. It's supposed to be a string. Number of bytes, we turn into bytes, and then we can do stuff with it. Okay, good enough. So this is gonna be, sure, string head and string argument. That's correct. And we'll read it because it's encoded as string. Table name is encoded as a string. Okay. Right, and we can say the same thing. Non needs a null value. Okay. And this one is a string. So we get that. We make sure that expected a string for a table name. Okay. Tag number 7. Yes, 7. There we go. And number of bytes is this and that. We read the bytes, and then we basically need to assemble the thing out of bytes. This is a decoder. So I can just do return bytes to surreal table. It's supposed to work. To surreal table. And we just take open array of uint. So it should work. There's a chance it works. So we're going to test that. So first of all, new encoding test. Test CBOR encoder table.net. Okay. Yeah. So again, as comparison, we can take the one that was for a string. So for table CBOR encoder table name, I'm gonna put in here. So basically encode simple table name. So we're gonna make it into maybe something like a table name could be located at, right? For a relation, for example. So we encode it, okay? Get the name, and we need to check if it's all correct. So first of all, we've got a tag, and this needs to be number 7. So 6, and with that is 7. Good. Then we need to have our 0b011 for type 3 for a string, and a length, which will be 10. 1, 2, 4, 8. So it'll be 8, and 2 should give us 10. All right. And we just need to grab this and just turn it into some kind of something. Bam. Just like that. Okay. I think that's it. Just encode a simple table and make sure that this is it. So if that's the case, we should be able to test this file, or we're missing something. Oops. What's wrong now? Okay, some different encoding seems to happen. 106 and 199.106. Oh. Wait. This is a table name as a string. Oh, wait. Okay, to add. So this needs to be TB for table. So we need table name. And now it's fine. You just need to make sure it's actual table. Great. So that's good. I mean, yeah, that's it. So that's it for that test. Now let's go and get the other test. So it will be for decoding. Test CBOR decoder. Table.name. So on the right, we can open decoder for a string as a reference. Ooh, that's one of the old ones. Still uses this weird stuff. Okay, so it'll be decode table name. So we'll just say, come up with another name, which could be something like approved by. Okay. So that's good. And again, I do tab key instead of table everywhere. And it needs to be TB, so we need table name. At some point, I'm just gonna make like a types, or I mean, the whole main Surreal thing will be able to export some things, but that's when we only when we settle on all the things, and then I'll be able to simplify all those imports greatly, especially from the perspective of end user at some point. So we've got our table name, right? So we want to decode it. So I'm just gonna get a new writer. Oh, and we're doing it manually. Ew. Ow. Oof. I mean, our encoder is already tested, right? So no, I'm not gonna get tempted. So where's my test for encoding the table? Okay, somewhere here. So I'm just gonna straight up take those bytes because they should be correct as far as I know. So let's say that constant bytes is this, and therefore I want decoded those bytes. Check if it's a real table, and when we get it, it's the same thing. Okay, that's literally it. And we don't need the writer anywhere, right? I mean, we don't have a writer here, so what is complaining? Writer is declared but not used. No, it's not. Unless it's complaining about that one or encoder. Or types. Huh. This is confusing me now. Equals. Oh yeah, because we have double. Now cannot decode. What is the problem? Was located at? Oh, of course. So let me. We have 11 characters, so that'll be one more than here. Okay. 11, and we need to encode that. So this way we're gonna have different values for encoding and decoding and whatnot. So we've double the chance to find some potential errors. Not really double, but yeah. It's just a little better. Okay, that worked. So we can decode it. Again, these are all like minimalistic tests. I just want to make sure things somewhat work. So if that's the case, we can close them all. And what I want to do is go to our Nimble And we just added everything related to a table. So serial value, we're just adding table here. We are adding a table here and here as well. Okay. I think we're gonna just actually finish today. I'm not feeling that great for some reason. So we're gonna finish at this point. At least we move a little bit more forward, right? We got some tags encoded. The only thing I want to add is go to this file and just have, you know, the end-to-end test of this thing. So we had the none. And that was the previous one, none, right? Yeah, so now we can just have table name. So we go down, all the way down here. So let's do encode and decode table name. So it's gonna be table. What could be a fun table name? Public post view table. There we go. Some people might name it that way too. So we got our table name. We're gonna for record users. The reason is why I'm making it so long is that this will trigger different way of encoding strings, and that should be another test. So let's encode that, decode that, and check if it's all the same. Okay. So when I write, I can't test it because I also need to import table name, at least for now. Okay, good. So this has been tested. Great. So we added all those things in here. So let's just push the code and finish for tonight. All right. So decoder, yes, encoder, yes, surreal value. Yep, sure, it's good. Table here is as the types values table. Private types values table. Why does it show only partial addition? Wait, I'm clicking the wrong one. This one's good. This one, added all three, and we have our tests, and basically surreal table name, coding, decoding, tests. Okay, let's push it, and let's call it day tonight. All right. All right. So it was really short today. Sorry about that. But again, we got some things working. We'll keep the pace going. By next week, we might actually have CBOR running and we'll be able to test it. And I would also like to add some basic benchmarks so that maybe we'll be able to capture some large amounts of data by running some queries, you know, varied data and whatnot, and then replay the same data in tests and run some benchmarks so that we have tests that not only, you know, pass or not, but we would have just, let's measure how fast it is or how something. And this way, as we're working on this whole thing, we can make sure that we're not slowing things down, we're just making them faster. Okay? And we can keep track of it, keep ourselves in check. Because the thing is that I don't know about NIM as much as I would like to, and that often causes me to implement things in not optimal way, or, you know, I don't have a lot of low level computer knowledge to feel comfortable with some things. So this would give us an opportunity to do things. And also, as you know, Hacktoberfest is coming, it would be nice to have some kind of way to maybe integrate it with GitHub and get some tests going to see if if things, like, oh, there's a pull request, and maybe GitHub will report like, okay, this took that long, and maybe it's that much faster or that much slower than the reference, because hey, maybe it could just write things into the file and unpublished to main kind of plop them there or something, update them automatically or something. I don't know. We'll see how that goes. We'll figure it out. But for now, thank you for watching. If you like the content, consider liking and subscribing. And you can also join my Discord. Link is in the description or down below here. And we'll continue on Monday, finally, with some more Unreal Engine and C++, and we'll continue our inventory system. Other than that, have a great weekend, everyone. See you around.